All right, so then knowing that certain gases can absorb infrared radiation is one thing, but being able to predict climate change based on the concentrations of these gases in the atmosphere is very, very difficult. Okay, there's some serious complicating factors when climate scientists start to try modeling. They try to come up with computer models, which is really mathematical equations, where they can put all the factors into the mathematical equations to try to calculate, how much heat is going to be absorbed by these gases and how it's going to cause the global average temperature to change. And so it's actually a very complex system, and you'll find that there's factors surrounding the oceans. You should have several reasons why the oceans complicate things. You should have several reasons why particles in the atmosphere complicate things. And when I say particles, particulate matter, such as smoke, haze, aerosols, soot. You should know how those complicate the models. Something called albedo. You should know what that means and how that complicates the models. And then population growth. Okay, so you all together should be able to find this information in your textbook. So working in small groups, you should have come up with these four factors, and you should know what it is associated with each of these factors that complicates the modeling of climate change based on the concentrations of greenhouse gases. Okay, here's an example of some results from some computer models, which is just mathematical equations to try to include all of the factors that affect global warming. And these are this particular model is based only on natural causes of greenhouse gases, and this one's anthropogenic. This is just the human factors, and then this is both of those natural and anthropogenic combined into one model. And when they talk about these computer models, they use this word forcings, and forcings are the factors that affect the model. Okay, so forcings are factors that affect the annual global mean surface temperature, such as tearing down more trees, or the snow melting and there's more dark surface for more visible light absorption to turn into heat energy, that kind of a thing. Okay, and so these are natural forcings, anthropogenic forcings, and these are all forcings combined. And what you see is on these graphs is the temperature change compared to the average temperature at some point in time, the temperature change over time from 1850 to 2000, and what you see is that there's the blue line is the model, the red line is the observation. So in each one of these graphs, the red line is exactly the same. Those are the observed temperatures over time that have been plotted from 1850 to 2000. So the red is data, real data, just temperatures. And the blue is models. Trying to just use natural causes, you cannot account for the increase in temperature. Trying to use human, it matches on better over here. When you compare all forcings in this particular model, the model is actually pretty good because you can see it's tracking pretty well with the actual temperature, and it's showing the increase over the last 10 or 20 years, tracking pretty well. So the reason why you want to have a model is you can then predict if the forcings all stay the same. You can predict what the temperature should be, or if you're able to change something like limit the amount of carbon dioxide emissions, for example, then you could adjust your model accordingly and show, oh, if people do this particular X, Y, and Z to change their habits, we may be able to bring this trend down and not continue the trend up. Okay, because it's this additive effect. You keep putting more and more carbon dioxide into the atmosphere, the oceans and the plants cannot reabsorb it fast enough. Okay, so that's just an example of a computer model.